Yeah, great. So today I want to continue a series of talks about homological algebra in Grothendieck topoi. As it turns out, I grossly overpromised the contents of today's talk, so I guess we'll only scratch the surface on the first topic that I declared as the contents of today's talk. Namely, we will talk a bit about Cech cohomology, but the large part of the talk will be dedicated to just some functoriality properties of cohomology of topoi. So I apologize for that in advance. And let's begin. So first of all, let's talk a bit about an ad hoc construction of derived functors between abelian categories. So it's all quite standard, I guess, and not very exciting because we use some very ad hoc tools to construct derived functors, but nevertheless, here it is. So assume that we have an additive functor. Okay. So assume that we have an additive functor between two abelian categories, and assume that it is left exact, meaning that it, well, you know what left exact means. We have an exact sequence, and the exactness property is preserved from the left. Then we say that a subclass of objects in this abelian category A is adapted to F if the value on an acyclic bounded below complex with objects from R is acyclic. So the value of F in such a complex should be acyclic. For example, of course, we can consider the class of injective objects. Then it is adapted to the functor F if the category has enough injectives, because another condition that we require from the class which is adapted to such a functor is that any object can be embedded into an object from this class R. So obviously, this definition suggests that this class should be used to construct, injective resolutions sorts. Well, I guess just resolutions. There is also a term co-resolution used for this kind of stuff if we consider a resolution from the right. Yeah, okay, so assume that we have so this is the definition of adapted classes of objects. And then
sorry, what is the
yes.
In the previous slide, what is the E?
E is just some object from R.
It exists?
Yeah, it should exist. So exists for any A, exists E such that, exists an embedding of A into E. So, but basically, if it's a class of injective objects, then category has sufficiently many injective objects if this is satisfied. Yeah. Okay. So now let's define derived functors for left exact additive functors between abelian categories. So by this D plus, we denote the usual derived category of bounded below complexes on A or B, and RF is the right derived functor, which is the functor between the derived categories of chain complexes on an abelian category, and on an object that is defined like this. So we take an object, we take its R resolution. So R resolution is a resolution which is constructed by, well, in a standard way. So if we have, okay, I guess maybe it's good to recall the construction of a standard resolution. Well, not standard, just of any resolution which involves this class R. So let me add a slide and briefly recall this construction. For some stupid reason, I decided not to do it originally, but I guess it's worth doing. So assume that we have an object A. For simplicity, I will assume that it belongs to the abelian category, although a very similar construction can be performed for chain concepts over this same abelian category. Then by assumption, we have an inclusion of A into some object E, which belongs to R. Then we can take this to be the first stage, so the zero stage of this resolution. Then we have the co-kernel of this map. And it also embeds into some other object E prime. This can be called the first stage of the resolution, and so on. And obviously the morphisms between the stages form a differential. So this is a pretty standard construction of a resolution for class of objects. And so we can apply this construction to see that we can define the right derived functor on an object using this formula. Okay, so I guess a less ad hoc construction of the same thing would be the following. So assume that we have two homological categories, C, W, and G, V, meaning that subcategories W and V are wide, meaning that they contain all isomorphisms, and they satisfy a 6 for 2 property. Then for an arbitrary functor from C to D, not necessarily a homotopical one, the right derived functor is a universal right approximation to F from the right. So this means that, well, a right approximation is just a pair consisting of a natural transformation and some functor. Or we can restrict G to be a homotopical functor. And then a universal right approximation is basically a homotopy initial functor in the under category of homotopical functors under F. So that's the conceptual way of defining the right derived functor, and it can be shown that this construction by resolutions provides precisely such a right derived functor. Okay, so now having said all that, we can define a Grothendieck spectral sequence. So the setting for Grothendieck spectral sequence is the following. So assume that we have 3 abelian categories and 2 additive functors between them. And we will assume that F and G are both left exact. Then we denote by RF and RG some classes adapted to F and G. And we assume that the image of RF is a subclass of RG. Then, of course, well, by the previous discussion, we have right derived functors of F and of G. And also we have the right derived functor of the composition and an isomorphism between the right derived functor of the composition and the composition of right derived functors. This is also quite standard. You can deduce it either from this discussion about homotopical categories or concretely using resolutions. So this is just a theorem about derived functors that's pretty standard, and it follows from general homotopical results. No spectral sequences here. However, this isomorphism between composites of derived functors and the derived functor of the composite give rise to a spectral sequence, which is constructed as follows. So assume that we were in the previous situation and assume that an image of any injective object in the category A is G acyclic. So obviously, yes, yeah, this notation sucks. What I meant to say was for any object which is a chain complex of injective objects in A. The image is G acyclic, then for any, this means that if we apply G to this complex, we obtain something acyclic. Then for any A object of A, there is a spectral sequence called Grothendieck spectral sequence, such that its E2 page looks like the values of P's derived functor of G composite with Q's derived functor of F on A, and its E-infinity page abuts to the right derived functor of the composite. So this spectral sequence appears in many places. So, for example, the Leray spectral sequence is an instance of Grothendieck spectral sequence, and many others are as well. So, why do we care about Grothendieck spectral sequence? Well, obviously because we can apply it to geometric morphisms of topoi and the induced functors on the categories of abelian objects. So the existence of a Grothendieck spectral sequence yields the following result about contrariality of Topos cohomology. So assume that we have a geometric morphism of topoi, of Grothendieck topoi, because, well, actually, we don't necessarily require there's to be a morphism of Grothendieck topoi. It's just necessary for both of them to have enough injectives. So if we have just some elementary topos with enough injectives, then it's okay. And assume that we have an abelian group object in E. Then we have a canonical morphism between cohomologies valued in A and in the pullback of A. So we have a morphism like this. I guess this can be interpreted as just the pullback. Well, if you think of topological spaces, for example, this can be interpreted just as a pullback of cohomology. So yeah, that's pretty standard. And more interestingly, we have the Leray type spectral sequence, which obviously derives from Grothendieck spectral sequence, which looks like this. So assume that we have an abelian group object in F. Then we have a spectral sequence which is functorial in B, such that it converges to cohomology of F with coefficients in B, and its E2 page is like this. So it's cohomology of E in degree P of the well, sort of cohomology of so this is the right derived functor of the push forward of B in degree Q. So once again, if we think of topological spaces, then this is just the standard Leray spectral sequence. So this becomes the cohomology of the base space. So E plays the role of the base space, and this becomes the cohomology of the fiber. Well, sort of. Actually, of course, we'll have to think of an appropriate local system, but actually in this language it is evident how all of this works, because this local nature is encoded by the construction of the Topos cohomology. So one way to derive an array spectral sequence is to apply Grothendieck spectral sequence to the induced morphism of sheaf topoi for topological spaces. A very simple and elegant way. Okay. So let's prove this result. Obviously, for E and F, we have two morphisms of topoi, which are induced by Honen from the terminal object of E or F respectively into an object, and this gives us a geometric morphism of topoi. So, yeah, I've written it already. Sorry. So this corresponds to this functor. And we have an actual transformation from the identity functor to the composition like this. So F was the original morphism of topoi, and this is just the unit of the adjunction. Then we have a functor like this between categories of abelian group objects in E and just the category of abelian groups. And this functor is exact and connected, meaning that it well doesn't lower the connectedness of an object. Then this means that we can apply, also it means that we can apply gamma lower star to alpha, which is this unit of the adjunction, and obtain a transformation like this. We have, well, an equation like this. And so this transformation extends to a transformation from the right derived functor of gamma lower star to the right derived functor of delta lower star F upper star. So and now it just remains to apply this natural transformation to well, specify it for concrete abelian group object A, and we get the desired homomorphism between cohomology groups for A and F upper star A. For the second part, or this Lurie type spectral sequence, we just need to apply the Grothendieck spectral sequence to the two functors like this. So we take a functor between categories of abelian group objects in F and E, and then the functor into the category of abelian groups induced by Honen from the unit, well, the terminal object in E. And this is isomorphic to this functor by the previous theorem, and also the Grothendieck spectral sequence yields precisely the Lurie spectral sequence that we stated in the formulation of this proposition. Okay. So another functoriality property is the following. So assume that we have a geometric morphism of topoi where E is a Grothendieck topos, and assume that we have an abelian group object in F. Then the derived functor of the push forward map coincides with the sheafification of this pre-sheaf. So we can consider a pre-sheaf which takes on an object U of C, takes the following value, and this is precisely so if we sheafify it, we obtain precisely the sheaf like this. So this is some kind of a push-pull construction for topoi. So let's prove this. So first of all, we first consider the situation where our topos is just the pre-sheaf topos, so the Grothendieck topology is minimal. Then this evaluation map on abelian group pre-sheaves is exact because the topos of pre-sheaves is Boolean. This means that the functor like this is the derived functor in degree Q of the functor like this. So it's a zero cohomology of the topos F on an object, which corresponds to the pullback. Yeah, it's unintelligible, I guess. But it corresponds to this. So it's a cohomology of the topos F on the object, which is a pullback of the unit embedding into the category of pre-sheaves of the object U. And this means that the result holds for a pre-sheaf topos. So in the case where our topos is Boolean, it is clear. Now we can consider an arbitrary sheaf topos, and we obviously have a geometric morphism from sheaf topos into a pre-sheaf topos induced just by the inclusion. So now we can denote by G the composite of this inclusion morphism and F, and we get the following. So so iota upper star G lower star is equal just by construction of G to this, and since iota upper star iota lower star is just the identity because sheafification is a reflexive localization, or the inclusion of the sheaf topos is reflexive. We get an isomorphism with F lower star. Also, I upper star is exact, so the I upper star is precisely the sheafification morphism is exact, and because sheafification is exact. And this means that if we take the derived functor degree Q of F lower star, it is by this equation the same as taking the right derived functor of I upper star G lower star. And by exactness of I upper star, we can pull it out of the derived functor and obtain this. And as we observed, iota upper star is precisely the sheafification functor, which means that G upper star of the unit embedded of U coincides with F upper star iota upper star of the same thing, and this is the same as well. This is precisely what we wanted. So here we have a certain clash of notation, but it's justified because we consider subcanonical topologies, and the sheafification of a unit of the unit embedding does nothing because all representable pre-sheaves are sheaves. So we obtain an equation like this, and from that we derive that we actually have an equation like this in an arbitrary topos. Okay, so that was just some very basic functionality properties that we didn't cover last time because we were so involved with set theoretic nonsense. But now let's consider a somewhat more concrete construction. Only somewhat, because it's completely useless for any sort of concrete computations, but nevertheless it's important just as an abstract tool of showing something about resolutions. So basically what we will describe now is a sort of minimal way of constructing resolutions which is closely related to the classical Guadamano construction. So that's just basically the Guadamano resolution for topoi. So assume that we have an abelian group object in a topos. Then we say that it is flabby if for any object in the topos, the cohomology of this object with coefficients in A is 0 for degrees higher than 0. So that's very similar to the usual definition of a flabby sheaf from classical sheaf theory. And such flabby sheaves can be used to construct resolutions, and it is done all the time in when we deal with the classical sheaf cohomology for manifolds, for schemes, or whatever. And now let's investigate how flabby sheaves or flabby objects, to be more precise, behave under geometric morphisms of topoi. So first of all, assume that we have some geometric morphism. Assume that we have a flabby abelian group object in F. Then once again, so A is acyclic for this functor, meaning that if we apply F lower star to A, then its higher cohomology group vanish. And also F lower star of A is flabby in E, so it's a stronger property. Here we only want to say that the higher cohomology groups vanish on the terminal object, and the second statement states that it actually vanishes on all objects of E. So let's prove this. So by the previous lemma, we have the following identification of a right derived functor, or well, the family of right derived functors with the family of sheaves constructed like this. We can apply the Grothendieck, and we see that since A is flabby, then this is just some object in F, which means that these cohomology groups are 0 above degree 0. So now we can apply the Grothendieck spectral sequence to see that its E2 page has only one row. So all rows above degree 0 are 0, because as we saw, this sheaf is 0 above degree 0. And in the row number 0, we have cohomology groups like this. Okay, but we also know that this spectral sequence abuts to the cohomology of F with coefficients in A, which is 0 for P plus Q greater than 0. And this necessarily implies that the cohomology groups vanish for E greater than 0, which means that A is acyclic, just as we want. Now let's consider an arbitrary object in E and consider the functor of the home functor from X in the topos E. Then we can consider a geometric morphism induced on the slice topoi and apply the Beck's commutativity lemma, which we discussed last time, to see that we have a nice morphism of functors like this. And now this allows us to apply the previous result. So we reduced the relative case to the absolute case, as is often done in such questions about cohomology. We reduced the question about some relative cohomology group over some object to cohomology groups over the terminal object. So we reduced it to the first part of the lemma. And this shows that flabby sheaves behave well under geometric morphisms. So an image of a flabby sheaf is flabby. Okay. So now we can construct an analog of the, yeah.
So, sorry, we have in the previous slides composition and why we have why have we obtained why we are done. I don't understand. We have a bottom isomorphism, and from this one we obtain what?
From this one, from this isomorphism, we see that to compute the cohomology of an object X with coefficients in the one moment, but the coefficients in the push forward sheaf F lower star of A, it is actually sufficient to compute the cohomology with of the topos A over X with coefficients in this sheaf, and this means that we can apply the previous result. So the idea was that.
And why is it flabby?
Well, because it was so it was we showed that if we have a flabby sheaf, then its image in the other topos is acyclic, right? So it means that it has no higher cohomology groups when we take cohomology over the terminal object, right? That's the first part of the lemma. The proof used this special sequence argument. Now we can just say that okay, now we want to prove it for an arbitrary object, and we can reduce it to the case of the terminal object because we can restrict to the slice categories. So what happens here when we pass to the slice category here, we obtain once again a flabby sheaf, because if the sheaf was flabby in a topos, it is clearly flabby in all slice topoi as well. And here we and to see that it is acyclic here, or equivalently, well, flabby because we chose X to be arbitrary. We just need to apply the previous result.
Okay.
Yeah. Thank you for the question, but I mean, yeah, maybe it's I don't know, maybe it was not as detailed as it should be, but yeah, the idea at least is that, so we can reduce the case of an arbitrary object to the case of the terminal object. Okay, so now let's discuss the Godeman construction for arbitrary topoi. Well, actually, I'm not sure that it is appropriate to call it the Godeman construction. Maybe it's more appropriate to just call it, I don't know, whole bar construction. But nevertheless, the idea is the same. So assume that we have a geometric morphism of topoi. Then we have a monad which corresponds to this adjunction. For this monad, we can consider a co-bar construction like this. So it's a co-augmented co-simplicial object in the category of abelian group objects in E. So this is just the unit of the adjunction, and then we have units of the adjunction which give us the co-phase maps. And so we can associate to this co-bar construction a co-chain complex by just taking the alternating sum of co-phase maps. And this thing here is what, in a sense, can be called the Guadamon resolution for A. So let's see why is that. Well, first of all, if we apply the pullback functor of this geometric morphism, we obtain a contraction homotopy, which is given by the co-unit of this junction. So the pullback of this complex becomes a cyclic in abelian in the category of abelian group objects for F. Also, if F is surjective, then F upper star preserves the property that an object is a cyclic, and this means that actually this this complex was a cyclic from the beginning. So this is a resolution not only in abelian group objects of F, but in abelian group objects of E. And now we can see, we have the following theorem, which can be regarded as an analog of the result that the cohomology of a complex constructed from the Guadamon resolution is the same as the sheaf cohomology of a sheaf. So assume that E is a Grothendieck topos and F is a surjective geometric morphism such that F is Boolean. Then we have an isomorphism like this. So so here we have the cohomology of an object X in the topos E, and here we have the cohomology of the common set of this adjunction with coefficients, with respect to the same object and coefficients in A. I will explain in a minute how this cohomology is computed, but you can think of it as just some algebraic gadget that allows us to compute the cohomology, and it is analogous to the Guadamon resolution. Moment. So let's prove this. Assume that we have an object in E and an abelian group object in E. By definition, this thing is just the cohomology of the complex which is induced from F upper star of A. And since epimorphisms in a Boolean topos split, this means that F lower star preserves the epimorphisms, and this means that F lower star is exact. But also F upper star is always exact. So this F large dot is an exact functor on the chain complexes of abelian group objects in E. Okay. Also, we know that assume that we have I don't like the fact that I denoted it by the same letters, so maybe that led to some confusion. But okay, so first of all, observe that if we have an abelian group object in F, then it is necessarily flagged because it is a Boolean topos, and last time we saw, we just stated that in a Boolean topos, all objects are are projective, meaning that any abelian group object is flappy, so there are no higher cohomology. Since A is flappy, when we apply this Fn of A, it is also flappy. And this means that this functor is exact. So the cohomology of this form is the same as cohomology of this. So yeah, these are the same functors. And now we can see that if we have an injective abelian group object in E, and we consider just some splitting suggestion from splitting epimorphism from TA, where T is the monad associated to the adjunction, into A. So this is splitting for this unit of the adjunction. Then we can apply the nth power of T to this splitting morphism and obtain a contracting homotopy for this co-chain complex, which means that this cohomology is
sorry.
Yeah.
Recall, please, what does it mean, splitting morphism?
Oh, that just means that the composition is identity. So, yeah.
In usual sense.
Yeah.
Okay.
No. And such splitting exists precisely because A is injective. Yeah. That's the reason. Yeah, so we obtain a contraction homotopy, meaning that on injective objects, this cohomology vanishes in higher degrees, and this means that sort of by the universal property, if we apply this cohomology to an arbitrary abelian group object, then this will just coincide with the direct functor of the home abelian group of X. So this shows that the cohomology of this topos E, of an object in topos E, can be reconstructed from cohomology in this Boolean topos F. The idea is that, and let's see a concrete example of this. So the first application is the Guedemann resolution itself. So assume that we have the topos E of sheaves on a topological space or on a locale. Then we can consider the Boolean topos of sets over X. So I guess another way that this is stated in, I think, this text project is that we can consider the morphism from the discrete topological space on the same set into X, which is always continuous, and then we can consider an induced morphism of sheaf topoi. And so the sheaves on this space form a Boolean topos. So we are in the situation of this theorem, and this means that we also have this. So we have this resolution, which coincides with the standard Guedemann construction, where we take in degree 0 the product of stocks on an open subset, and then the next stage is defined as the co-kernel of the morphism from the previous stage. So that's the standard Guedemann resolution in this Topos theoretic terms. But we also can obtain something else. So another application is to continuous representations of topological groups. So assume that we have a topos of continuous set representations of G. Then this resolution in degree n consists of continuous maps from G to the power n plus 1, where G acts by translation on each factor. So G on G1, I guess G0, Gn is G0, Gn. So this is obviously a continuous G set, and this is well, also a continuous G set. And we can consider just continuous, not necessarily equivariant maps between the two. This produces this analog of Godel resolution, but for continuous representations of a topological group. In particular, if we take a discrete topological group, we obtain precisely the usual bar construction for G and some G modulo A. Okay, so now we arrive to actually the longer topic that somewhat interlaps with what I promised at the abstract, but it's the very last part of my talk. So I want to start talking about Cech methods. Obviously, we won't be able to cover them all today, but just some first ideas about this. So first of all, now we restrict to the case of a Grothendieck topos. And the idea is that while in the previous discussion, we tried to construct some resolutions using just geometric morphisms and monads on this topos, so we didn't use in an essential way that it wasn't a Grothendieck topos. So this was possible in an elementary topos which has sufficiently many injective objects, or if we want to be very specific, some class of sufficiently many objects adapted to this precise geometric morphism. So we didn't really care about this side structure of the underlying category for which this is a sheaf topos. But now the Cech methods are concerned with computations that involve in an essential way this side structure. So we want to know something about sheaves by sort of approximating them by representable sheaves. Obviously there is a representation as a colimit of representables, but it is not very useful for calculations. So there is this another approach which yields Cech cohomology, for example. So assume that our site is a category with pullbacks. Otherwise, it would be hard to apply this Cech method directly, although it is possible to use hypercovers instead of Cech covers, which we partially covered in the second talk of this semester. So assume that we have a covering of an object U indexed by some set gamma. Then a Cech, I guess Cech simply show sheaf is the nerve of a groupoid which is defined like this. So we have the co-product of all elements of this covering, and we have the co-product of all fiber products of the elements of this covering, twofold fiber products. And we have morphisms which are induced by the projections from the pullback. Okay, then we can take the nerve and obtain the simplicial sheaf. It is indeed a sheaf because the topology was subcanonical, and the sheaf condition is checked degree-wise. Okay, so what we will discuss now is applicable to arbitrary sheaf topoi, in particular to the largest sheaf topos, namely of all pre-sheaves. Note that the category of abelian group objects in this topos is a category of algebras over the linear theory AB. And this means that we have the free functor from P to the category of abelian group objects. So that's the property of algebras over linear theories, that we have the free forgetful adjunction. So the forgetful adjunction just maps an abelian group object into the value on the generator of the category F, and the free functor exists by some general results about, well, by the general adjoint functor theorem. So now we can apply this free functor degree-wise to our simplicial sheaf, or simplicial pre-sheaf in this context. And then we can take the associated co-chain complex or chain complex with the differential which is given by the alternating phase maps. So one of the cornerstones of this Cech theory is that we obtain something acyclic. So in a sense, this is a prototypical Cech resolution, and this lemma justifies the name resolution. Well, so I just remind the notation. So U is a covariant, U gamma are elements of the covariant family, and theta gamma are maps in this covariant family. To prove this lemma, it is enough, of course, to check exactness of this complex of sheaves of abelian groups, or sorry, of pre-sheaves of abelian groups on objects of our site. And since the evaluation functor from the category of pre-sheaves to category of abelian groups, well, in general to sets, but since we're dealing with pre-sheaves of abelian groups, we land in the category of abelian groups, is a left adjoint of the corresponding morphism of topoi. This means that F upper star commutes with this free functor. So two left adjoints commute. And this means that actually the value of F upper star on this complex of pre-sheaves coincides with the free functor, but in category of sets, on F upper star of this simplicial pre-sheaf. But this can be computed very easily. It's just the free functor in sets on disjoint union of, well, on a simplicial set like this. So sigmas go over gamma to the power n, and these are just the corresponding fiber products. Okay, but this can be simplified even further. So denote by S phi for a morphism from V to U. the co-product over all elements of the covering family of the morphisms over U from pi to theta gamma. So these are just transformations or morphisms, morphisms over U. So triangles like this. Now we can apply the universal property of a fiber product to see that actually this simplicial set can be represented by this. So it splits into disjoint unions of S phi's for different gammas. Okay. But since our category of abelian group objects in a Grothendieck topos satisfies the conditions on the Grothendieck abelian category, which we showed sort of last time, the co-product of exact sequences is once again an exact sequence, which means that we can restrict our attention to a simplicial object of this form. So we just take some set and we take its powers and we form a simplicial set like this, where the phase maps are given by projections from Cartesian powers of the set. And then we can show that the resulting chain complex is acyclic in two ways. Well, I guess one way reduces to another, but first of all, we have a very hands-on demonstration of this fact. So we can just pick an element in S and construct a contracting homotopy like this. So that's one way to see that the complex is acyclic, proving the lemma. And another way is to apply the fact that the free functor is a left Boolean functor from simplicial sets to chain complexes, and such complex, which corresponds to powers of a set, is actually homotopy equivalent to a point which the left Boolean functor and compute its homology, we obtain homology of a point. So, I guess that's another way to see the same thing. And now we can define what is the Cech cohomology in topoi. So assume that we have an abelian group object in the pre-shift topos. Then we can define what is the Cech complex of this, of a covering for an object U. So this is just the complex which corresponds to this. So we have this complex, and then we home from it to A, and we obtain a complex of abelian groups. And since this complex consists of three objects, this means that we can present the Cech complex as a complex of products like this. So this looks very much like the classical Cech complex for, say, topological spaces. And finally, we can define the Cech cohomology groups over covering with respect to, well, with coefficients in an abelian group object A as the homology or cohomology of this co-chain complex with the Cech differential, which is just the simplicial differential induced from this simplicial object. I guess I want to end by stating this obvious example. So assume that we have a Grothendieck topos of sheaves on a topological space, then the Cech cohomology of the a covering in this topos is just the usual Cech homology of a sheaf on a topological space with respect to some cover. So I also wanted to give an example related to this category of continuous G sets, but unfortunately, I wasn't able to produce, I wasn't able to produce some non-trivial example of Cech cohomology for this topos. So clearly we can consider the following stupid example. So take, since this topos of continuous G sets is actually a topos of sheaves on an orbit category of G with atomic topology, this means that a covering is just any morphism between any morphism in an orbit category. So if we take, for example, the terminal object, there is a unique morphism from any subgroup of G. If we consider continuous G sets from any open subgroup of G. And then the Cech cohomology of such covering is quite stupid. It's just it coincides with global sections of such coefficient system on H. So it would be interesting to consider some more meaningful computations where Cech cohomology actually produces something non-trivial. But in 10 minutes I had before giving this talk, I was not able to produce such an example. So maybe someone can think it up or read it somewhere and present it to us. Or maybe I will understand how to do this, and we will discuss it in some future talks. Okay, thank you so much for attending today's seminar, and I hope to see you all this Friday. Let me stop the recording, and maybe we can discuss something.